Good morning. Welcome to the third plenary lecture in APS 105. It's my pleasure today to introduce Dr. Inmar Givoni. She holds the position of Vice President of Big Data at Kobo. Hands up if you've heard of Kobo. Do you know which university founded the company Kobo? Not Harvard, no. University of Toronto, graduate in mechanical industrial engineering, started Kobo. It was sold to a Japanese company a couple of years back, I believe. Kobo is an e-reader company, and I would normally give you Inmar's biography, but in her talk she's going to tell you how she arrived, starting in high school, to here, and so I won't do that. I'll just say one of the reasons this topic is really interesting is that in the last 2 to 4 years, one of the most important topics being talked about in technology and in startups has been machine learning, and in particular something called deep neural networks, which were invented or really pushed here at the University of Toronto. Professor Jeff Hinton was the one who kind of noticed there was a much better way to do artificial intelligence. And so this university is very strong in this area, and Dr. Givoni comes from a student of Professor Hinton's, and so it's a particularly important and very interesting topic, both intellectually and economically. So that's all I'll say. Please join me in welcoming Dr. Inmar Givoni. I'll stick this up here. There you go.
Okay. So hopefully both of them are on and you can all hear me. Up at the balcony? Yeah, great. Okay, good morning everyone. And let's start the laptop. Good. All right. Good. Okay. So it's early morning on a Wednesday. Thanks for showing up. So my name is Inmar, and I'm going to tell you a little bit about machine learning and big data and some of the things that we do with it at Kobo. But as Jonathan said before that, I want to sort of tell you a little bit about how I got to where I am, and hopefully you might find it interesting. So quite a long time ago, I went to high school. I went to a high school that was pretty intense on the sciences and math, and we were encouraged to take as many different topics as we wanted. And I really liked physics, I liked math, chemistry, and I also decided to take programming language courses. And the truth is, I didn't quite get it. So I could, I understood what was being taught in class, I understood the concepts fairly well, but then when I needed to go and deal with the IDE and the compiler and the debugger and so on, it didn't really make all that sense to me, and I never felt I really got to the bottom of it. What I wanted to do back in high school, I thought I would be a neuroscientist. I thought that understanding the brain is one of the most important and interesting questions that we could tackle, and I really imagined that I would grow up to be a neuroscientist, and I would prepare for that with the topics that I chose at school and university and so on. So after I was done with high school, and still, taking with me the sense that I didn't quite understand programming and computer science, I went to the army. So that's what we do in Israel. I'm from Israel originally. So men and women are enlisted in the army. It's a mandatory service. And I spent a few years doing work for a unit that's very secret. It's got its own Wikipedia page. It's that secret. And I was working basically on intelligence. So I can tell you what I did, and then I'll have to kill you all, as the saying goes. But we won't do that. Instead, I will tell you that as part of what I did, I was working a lot with some technical teams that were developing software for us to use. The reason for that is, it's the intelligence unit. You cannot go and outsource what you need to do to some, third-party company and ask them to build the code for you. You need to do it in-house yourself. So the software developers I was working with knew how to develop software, but they understood very little about what it is that we were doing with that software, because they didn't go through the intense intelligence training that I and other people went through. So towards the end of my mandatory service, they came to me and said, well, we work a lot with you. You seem to understand the business of intelligence quite well, and you seem technically inclined. So how about we teach you how to program well, and you bring all that user experience knowledge into the picture, and that will help us make better systems. And to me, that was a great suggestion. That was a great opportunity, because I knew that this way I would be able to overcome this sort of fear or lack of understanding that I had with software development. And this is what I did. I spent a little bit of time retraining on coding, learning a bunch of different languages and different environments, and then I worked as a software developer in the Army for a few more years. And it was great. I loved it. I was working with great people on super interesting problems. But eventually, I decided to go back to study things more formally, and I went to university. So I went to the Hebrew University in Jerusalem. And I was still holding on to this idea that I wanted to one day be a neuroscientist. And I thought, what could I study that will prepare the path for me? And I thought, I'll study computer science, because now I really like it and I want to get a more formal education. But I will also study biology, because then that will relate to the brain and humans and the human brain and so on. And whenever I had a chance to take an elective in neuroscience, I did, and I did some summer work in neuroscience. And then on my third year of university, I took a course in machine learning. And that really blew my mind. I was so excited by this combination of mathematics, computer science, statistics, and the way that it all combined in a beautiful way to solve problems that were really, really interesting, solve problems that the brain is really, really good at solving. And that we as humans, writing it down in the language of software engineering, were not as good at solving, definitely not back then. And so I decided to shift path a bit, and rather than try to understand the brain, try to build machines that sort of mimic the brain. And so I came here to Toronto to do a PhD in machine learning. Now, Toronto is one of the best places in the world to specialize in machine learning and artificial intelligence. The computer science department and many of the members of the electrical and computer engineering department are part of this group, and they do some incredible work. I'll touch maybe a little bit later on some key people. And so I did that. I studied machine learning here. During my PhD, I did take the opportunity to go and do a couple of internships. And this is something that I definitely encourage all of you to do. I know that there is the PEY project that you can do, and also internships over summer. It's a really good way to understand what the industry is about, or what a research lab is all about, and so on. So I went to a couple of places. I went to to Silicon Valley. Microsoft had a research lab in Silicon Valley, not far from the Googleplex back then, and I worked on e-commerce on the back end of Bing search, and helping the search engine understand when you're trying to buy something, how to present to you relevant results. And I also went a year later to Cambridge in England and worked again at Microsoft Research on the Kinect system. So has anyone ever played with Kinect? Hopefully some of you did. Yeah, so Kinect, one of the first things that the system needs to do is to figure out where you are, where are your different limbs. This is called the pose estimation problem. So I was part of the team that looked at that algorithm. And finally, I graduated, and at that point, I've been in academia for quite a while, and I needed to just move on with my life and find a real job and start being an adult. And so I went and worked not far from university at Altera. So that's a company that Jonathan is well familiar with, and maybe we'll tell you about more in detail one day. And after about a year or so, I decided I really missed doing machine learning. And I went to Kobo. So at Kobo, I worked as an individual contributor, as a research scientist, working on all sorts of interesting problems having to do with the analysis of the text of books, and looking at the website and how to optimize it, looking at recommendation and search. I'll tell you a little bit more about that. So Kobo, okay, we'll get to that later. Anyways, so that was a little bit about my journey. And now let's talk about computers and why they're awesome and in what ways are they not awesome. So this is the young Bill Gates, and he's very young here. It's a very nice looking computer. What can computers do? Computers solve problems for us, basically. We might not think about it that way, but there are a lot of different everyday problems that we need a machine to solve because it'll be faster, more efficient, less tedious, less boring, and so on. So a very simple example will be just calculation, arithmetic. So everyone has a calculator on their cell phone. If they want to multiply and divide some numbers, they can do it. That's a problem a computer solves, even though it's a very old problem that we've had machines that can solve it that are not as complicated as computers. Here's another problem. You want to send a message on Facebook to one of your friends. And let's say that you have a lot of friends, right? If you needed to go and find a friend in the list of friends, it'll take you a while. You might first decide to sort the list, and that will take you, the first sorting will take you a while, and then it might be easier to find it. But really, what computers allow us to do is to start typing the name of the friend, maybe the first couple of letters, and the name of your friend pops up. You can click on it and send a message. So this ability to quickly search for things in long lists, to quickly sort things, is also a problem that computers solve very, very efficiently and very quickly. And you use a word processor. You go and write some homework. You have automatic spelling correction. That's another example of a problem that's very well suited for solving with computers. So there is a problem, though. There seems to be a class of problems, a class of challenges that are very hard to solve via traditional programming. So I know you're just starting your education in software development and programming, and you've learned about a bunch of things that you can do, if statement, for statement, or so on, and so on. And if you've tried solving some problem, some homework problem, you usually think about the problem, and there is sort of what I call a common sense way of solving things, right? If this, then do that. For how many every iteration, do something else. And that helps us with doing things like spelling correction and calculations and so on. You might have already gotten some assignments like that. But there are all these tasks that correspond to things that humans do very well that you can't really write down in that common sense way. You can't really capture. And I'll give you some examples. So here is something that I'm going to ask someone to read. Can you read this for me?
The face of a child can say it all.
The face, OK, just a little louder, sorry.
The face of a child can say it all, especially the mouth part of the face.
OK, so what happened here? First of all, we had we have a text-to-speech processing machine right here, which is perfect. It has the right intonation and everything. There's also the ability to understand that this is perhaps bad humor. So you all get that. Nobody laughs because it's really a bad joke. So there is a lot of speech understandings, and the understanding of sound, of phonemes that goes on here. And to get a computer to generate the sound of it in a way that sounds human, or to understand the subtle bad humor here, is quite a difficult task. Here is another thing that humans do very well. So, so can you tell me, hello. Yeah, I picked on you. Can you tell me what you're seeing here? He's kind of?
He looks bored.
He looks bored. OK, so we have two men. The right one is kind of bored. Or maybe is a little, bored, upset, some form of a negative emotion. He's definitely not happy and dancing around. So this ability to look at a short snippet of video and understand what's going on in this image or sequence of images, the fact that there are that many people, what they're wearing, are they indoor or outdoor in this example? They're indoor, right? It seems like one of them has two hands and the other doesn't. Would you say that the other doesn't have hands? Of course, yeah. Right, so he's holding his hands under the table, and we can infer that he has hands. We have no reason to speculate otherwise, but for a computer, if you ask how many hands there are, it will say probably two. So there are all these, yes, their gender. We can tell by their clothing that they're probably, not. There might be fake characters and so on. So this ability to understand an image and capture in, say, words, all the information in it is something that is difficult, again, for a computer to do. So why is it difficult? Let's think about the task of just trying to detect whether there is a face in a single image, okay? So if we were to do it in the standard common sense way of programming, we would probably go about it in the following way. We would say, okay, let's first look for something that looks like eyes. And if we found, but the eyes can be, we need to give it a range. So we need to say that the eyes can be some distance apart from one another. The size can be variable in different images. Okay, maybe if we found the eyes, then we need to search for something that looks like a nose. And then maybe a mouth, but the mouth can be smiling, it can be frowning. Then we might need to look for something that looks like hair, but the hair can come in a variety of colors. And the problem is, if we were to write it in something that is like if, then, and so on, using the construct that you're already familiar with, there would be just too many variations to list down. We cannot capture it in a way that comprehensively describes what a face is. And the truth is, we probably don't really actually understand the rules ourselves. We're very, very good at it. We're very good at detecting faces, but it's not like we have a clear understanding of how we go about it. And so there is a completely different approach to solving the problem. Rather than trying to state what should be found in the image, we use the machine learning approach. So at a high level, the way it works is that it learns from examples the way that children do. So you show it a lot of examples of different things, including faces, and you say, this is a face, this is a face, this is a face, this is not a face, this is not a face. And then you ask the computer, what is this new thing that you're seeing? And it'll say, oh, it's a face. And you'll say, no, this is not a face. Go back to your drawing board, and so on. So it's basically this idea of learning from examples, of using a lot of data for which you know the correct answer. This is what we typically call the training data. And then you do something with the data, which is the training phase. And once you're done training, then you can go and test the algorithm. And hopefully the results are good enough so that you can actually use it. And if not, you can always bring on more data, or you can make the underlying algorithm a little bit more complex, because maybe it's just too simple to capture what you're trying to do. So here is an example. We bring a lot of images of faces. We bring a lot of images of things that are not faces. And so the strategy is basically you gather all of this data. There's always a lot of data involved. Images with their true labels, so the label would be whether there is a face or no face in the image, and then you process them into something that is what I call machine-friendly representation. So an image is typically made up of a bunch of pixels, and each pixel has its RGB values associated with, and you can maybe dump every one of these numbers into this very, very long set of numbers that we like to call a vector. And a vector is a mathematical creature. We can start doing things like projecting it, multiplying it by matrices, and so on. So that would be what we would do with an image. Or maybe we would first extract some features out of the image and then represent those in a vector. If it's sound, then we'll need to take the sound and again translate it into some digital form that is easier to work with. And then we basically let the algorithm figure out the decision rule for itself. So that's at the high level what we call supervised learning. That's the sort of easier concept to wrap your head around. You show examples with the correct answers, and you get a yes or no answer. And there's also unsupervised learning, which is the same problem, except you don't even give the machine the labels. You just say, here is a group of data, and try to find common patterns in it. So an example would be if I give the machine a lot of images and I say there are actually 3 types of groups. Maybe it's images of dogs, cats, and dolphins. But I don't tell the machine that this is a dolphin and this is not a dolphin. I just tell it, try to separate out the different items so that within each group there is a lot of similarity, but between different groups there is a lot of dissimilarity. And that's typically referred to as unsupervised learning, because it doesn't really know the true label. So where is machine learning used? Machine learning is currently used almost everywhere. That wasn't the case 10 years ago, and it wasn't that much of the case 5 years ago. But now, if all of you probably have cell phones, pretty much every application you use has some form, some variant of machine learning. But let's go over some common examples. So you can talk to your smartphone. There's Siri or OK Google. All the speech processing and speech understanding uses a lot of machine learning technologies. You can use your machine to translate different things from language to language. Machine translation is typically based off of machine learning algorithm. We've talked a little bit about detecting faces. So detecting faces, detecting objects, recognizing objects, that's all machine learning. This is an image from Google Street Views. They've been able to detect all of the license plates in images and remove them for privacy reasons, so that's using machine learning algorithms. That's an image of a sloth. So again, the ability to detect different types of items, to categorize different types of items in images. So for example, those of you who use Google Photos, it will automatically tell you that these are images of dogs, cats, sloth, and so on. So that's object recognition, that's a machine learning algorithm. And even within PowerPoint, if you've ever used the background removal feature, that's using under the hood a machine learning algorithm. So these are all sort of tasks that, as I said, are typically very easy for humans. Up until the machine learning paradigm started to really to catch on, it was very difficult to do it through software development in the common sense aspect of the word. But it's also used for things that go beyond what people are necessarily good at doing. So every time you do a search, Google uses machine learning technologies to sort the results of your search in the best way for you. Robots and robotics use a lot of machine learning, so the agent can move around and understand and interact with what's in the room or the environment. Recommendation system. So recommendation system is an example of a machine learning algorithm that you probably use all the time. A lot of apps will suggest, things that you might like or you might enjoy, and it's typically based on your past behavior with the application. You see that on Netflix, on online dating websites. Kobo and Amazon both have recommendation systems for books you might enjoy reading, and so on. Spam detection. So spam detection is actually a really old example of a machine learning algorithm. It's been in use for quite a while because it's a relatively simple problem in the sense that you get a lot of data and you look at the words and you train it in the way that I've described before, or you show the algorithm a lot of positive and negative examples. Machine learning has now been integrated into a lot of medical applications around understanding medical images, understanding genomic data, and even something like your Facebook feed and the order of it and what things get prioritized or not is using some form of a machine learning algorithm. So hopefully you get a little bit of sense of what machine learning is about, and now I'm going to explain a little bit about what big data is. So who has heard of the concept of big data? Okay, so it's kind of a big buzzword. It's been in the past few years. But it's something that not a lot of people not everyone agrees on the definition. So I'll give you my understanding of big data and where it comes from. So right now, everyone is tracking and measuring everything you do on electronic devices that are connected through Wi-Fi, for example. So for example, Google knows everything you've searched for, every map you've looked at, what you email about, the videos you watch, and so on. And every one of these events is logged. Facebook knows everything about what you've liked, what you posted, what articles you clicked on, what things you said that you enjoy, like movies and so on, your date of birth, everything you tell it, it knows. Websites and apps. So you open a website, it tracks every little click you do, every little choice you make. It all gets back sent to the servers. And then the idea is that everyone is saying, oh, we have all this exciting data. We know what the users are doing. Let's use it for something good. Let's use it for something interesting. So everyone is trying to make sense of the data and make good use of the data. And in order to do that, because there's so much of it, you need a few components. So first of all, you need engineering for all of this large-scale processing. So you have so much data streaming in that just processing the data, just putting it in a form that's computer readable, that is easy to process, easy to digest, required a whole set of new technologies. And Google spearheaded that perhaps 10 or 15 years ago, and everyone caught up pretty quickly. It also requires that, so that's just processing the data, but what do you do with it? So usually there is some challenging problem that requires either a machine learning type algorithm or statistical type of approach, a modeling approach, if you're trying to predict something, for example. And then typically there is the domain-specific questions. So for a company like Kobo, it will be business questions around books and reading and so on. For a medical application, it would be some questions about the biology underneath it and so on. So, so for every company or every institution that tries to do big data, there's always the domain-specific aspect of it. And then the intersection of all these things is what I like to think of as big data. One of the things that really pushed big data to become such an emerging concept and a quickly emerging concept is that there is a very large community of people who contribute to open source projects. A lot of them are headed by Apache, and these are some examples of available systems for doing all sorts of things, for searching, for crunching through log data, for streaming data, for running all sorts of complicated computation on data, for scheduling a lot of different jobs with the data, for running machine learning algorithms on data, for storing the data, and so on. But when we're talking about large data sets, and the requirement is that we deal with tons of data and we do it quickly. And so the fact that we have all of this open source code available makes it very easy for people to start using big data even without putting a lot of money into it. And so the availability of all of this open source code has really made a significant difference in how easy it is to start using your data. And what do we do? Yeah. Yeah.
Say what open source is.
Oh, okay. So open source is basically when the code is available for everyone to download and use, sometimes without paying any fee. Sometimes there are some regulations around it, like you cannot use it for industrial purposes, or you can only use it for that much amount of data or whatever. But the concept in itself is the idea that someone wrote it for free and put it out there on the internet for everyone else to download and start using. And then some people just do it and publish it on public repositories. Maybe you've heard of something like GitHub. And some people do it as part of projects where they work together, they have deadlines, they have goals, but it's all volunteer work for the most part, and they're doing it just because they like coding, they like contributing, and it's actually one of the most beautiful things, I think, about the internet. So now let's talk a little bit about big data and machine learning, specifically at Kobo. So, just so we talk about what Kobo is. So as Jonathan mentioned, it's a e-reading company, and so we sell devices. This is the Kobo Touch is a device that came just like a couple of weeks ago. We also have a device that's water resistant and so on. And these are e-ink devices, so they're easy to read on and so on. But we also develop applications. So we have an Android app and an iOS app and a Windows app, a desktop application, so you can read on your desktop, if you will. And the philosophy for Kobo, at least, is that we want you to be able to read on any device, and we want you to be able to seamlessly transition between the devices. So the format we use for the files is the ebook format. So it's a well-established format. It's not proprietary to Kobo. That means that you can take it from one place, one device, and put it on another, and so on. Kobo as a company was founded here in Toronto in 2009, so not so long ago, and it was, after a few years, it was bought by Rakuten. Rakuten is, most of you probably did not hear of Rakuten, but it's a very large company in Japan. In Japan, it's kind of like the Amazon of Japan, and it's also looking at international expansion. So it's been buying and collaborating with a lot of companies worldwide in the past few years, and Kobo was one of the acquisitions towards having more of a digital media presence. And so these are some, these are the team members of the big data team. So a lot of us are engineers, computer scientists, undergraduate degrees, graduate degrees, a nice mix. A lot of them came from here, from U of T. So these were the people. What about the data? We deal with a lot of data. We have a catalog of about 5 million books. We have a lot of books that are self-published, so we allow people to publish their own books on the Kobo catalog if they so wish. The books are in over 140 languages. We have quite a lot of users. And then what do we track? What do we process? So everything you click on, everything you buy, whether you do it on the web or on the app, we get a message to the big data team and we put it in our servers. When you read, when you flip a page, when you look up a word, when you stop reading, when you search for a new book, when you use your recommendation, all of these activities we log and we try to make good use of them. And we can also look at the contents of the book. So every word in every book is ours to look at, to analyze, to consume, and to make some interesting use of. So here are some cool things that we do with all of this data. So as I mentioned before, we have a recommendation system. So this is a recommendation system that was built in-house. We look at what you've read. We look at what you browsed at. We look at the kind of previews you've downloaded. We looked at the reviews you've given us. And we use all of that information to recommend what we think is the best book, the next best read for you. We also, if you just go and look at a particular book, we also look at what other people who've read the book also read. And so we provide you a book-to-book recommendation. So the first type is what we call user-to-item recommendation. The second type is item-to-item recommendation. And you're probably familiar with this concept from a lot of websites and applications you already use. The way we do it is based on an approach called collaborative filtering. So collaborative filtering basically says, we have a lot of books, we have a lot of users. Some of the users already tell us that they like some of the books. And so we just try, when we try to find for a given book, for Gone Girl, a similar book, we basically look at all the users that have read Gone Girl, and all the users that have read other things, and we try to find the books that have the best overlap of users who've read both. And so this is the essence of collaborative filtering. Of course, the actual mathematics is a little bit more complicated, but that's the high-level gist of it. One of the things that we do that is slightly more interesting than that, because this is a very typical approach, very typical machine learning application, is sometimes we don't know about anyone who's read a particular book. There are some books in the catalog that no one that we know of has told us that they've read. And so how do we find related titles to these books if we don't know anything about the readership of them? And that's when we look at the actual content of the book. So we analyze the words of the book and we try to find using a machine learning technique called topic modeling, we automatically come up with a list of all the topics the book is about, and then we try to find other books that share the same topics through the analysis of the text. Search. So as I mentioned, Google uses machine learning for search. Everyone does, and so do we. So we use an off-the-shelf platform called Solar. This is one of these open projects that I touched upon before. And we search for, the user comes on the website and searches for a particular book. Maybe they type the name of the book and the author. And then we go into the catalog and find all the books that match that. But then the question is, how do we actually sort it in the best way possible? And to sort it cleverly, you need to take into account several things. You need to take into account how well the query matches what the book title and the author and the subtitle and so on. But you also need to take into account how popular the book is, how many times it's been sold, what kind of reviews it gets, and so on. So you can try and hand tweak some sort of a mathematical formula to answer this question, or you can say, I'll treat it as a machine learning problem, and I let the computer figure out what is the right way of combining all of these different signals together to yield the best search results for the user. And so this is just an example of showing how before we sort it, maybe some book was at the last position, but after we apply our algorithm, it comes to the first position. OK. One more interesting thing that we do is we try to look at the content of books and detect to what extent are they of pornographic nature. Now, why do we? Yeah. So a lot of our catalog, a considerable chunk of our catalog deals with what we called active romance. That's the industry term for it. And a lot of people enjoy consuming it, and there's no harm in it as it is. However, as I said, we do have a self-publishing platform where people are allowed to put anything they want to sell. Except we do have some policies around it. There are some topics that we don't want people writing about, not on our website. Now, is it just going to be a relationship of trust between us and the authors? It cannot be, because some people will violate the content policy. And so in order to make sure that we catch all of these things, we actually go and look at the content of the book and try to determine to what level is it pornographic. And we actually have established 4 types of labels. So we have the books that are completely normal. They're not in any way or form about adult material. We have what we call sexy, so this is where things like 50 Shades of Grey would fall into. So there is a little bit of action, but there is a plot, there is characters, there is some interest beyond just the sexual part. Then we have books that are sort of, they're only about one thing, really, and that's what they've been meant to, right? All of these are still fine. We just want to know the different granularities so that we can choose to not present some of the content on our kids' web store and so on. But then there are books who violate the policy, and I'm not going to show you any of these titles. And these books don't get to show up on the catalog at all. So before the book is actually published, we process the book, we determine the category of the book, and if it gets this label, then we say we're not actually going to put it on the website. Okay. Here's another problem that we try to solve. If you go to the website, you'll see that there are all sorts of lists of books that we present to the user. So here is an example. The first list you're going to see is what we personally recommend for you. That's if you're logged in. A second list you're going to see is the top 50 ebooks. So even that is an interesting problem, although we don't solve it with a machine learning strategy. We solve it with some statistics and modeling. How do you determine what are the most popular books on the website? So you can look at the total number of times a book has been sold over time, but that's maybe not as interesting because Harry Potter was a gigantic seller. We don't want to put it as our top item because right now people are not reading it. So how do you combine the amount of books that people are consuming of a particular title and when they did it so that you come up with the hottest books? So we have an algorithm for that, so we provide you with sort of what's the most interesting thing happening on the website. And then maybe there are other lists that are curated by humans, by the merchandisers. This is what we call them. So these are people who are book experts, and they sit around and decide on, for example, what are the most interesting new releases. If some author gets an award or some author passes away, maybe they will compile a list of the books by the author. So we have all of these different lists. And then there is the question of how do we actually sort them so that it's the most optimized experience for the user? And the answer is that it actually depends on the user, because different users have different tastes. And so one of the algorithms we use will take everything we know about you, the user, so what kind of books you read, in what kind of genres, what kind of things you browsed at. Are you price sensitive? Are you sensitive to new releases? Like, do you care more about new books as opposed to the entire catalog and the activities you've done on the website to try to order these lists of items to the best of our ability so that the chances are that you'll find something that you're looking for. So I mentioned that we look at how people read, and this is one of the newest and interesting projects that we're looking at right now. What this is showing you is averaged across all of our reading, the average reading time in minute for a particular time of day over 7 days. So let me see if I have, so basically each different color represents a different day of the week. And these are the 24 hours of the day. And this would be 8 a.m. in the morning, and this would be 8 p.m. in the evening. And this is the average time, reading time per user for that period of time. And so if you look at all of this data, you see some interesting patterns. You see that people do a lot of their reading time sort of in the evening, around 8 or so, that some people do some reading earlier in the day. You see, so this would be the weekend. You see more activity on the weekend. But generally speaking, there isn't a lot of patterns going on here. And so one of the things we did is we applied this idea of unsupervised clustering, unsupervised learning to all of the reading data to try and group our users into different cohorts of people who read in a similar fashion. And this is some examples of the cohorts that we are able to find automatically. So you'll see that this is a group of users that don't read much through the day, but they all kind of read in between 8 and 12, let's say. And you can see that this is very, very periodic with a little bit more reading happening on the weekend. These are actually, they read in quite an opposite pattern. They do most of the reading during the day, and then they don't actually do anything at night. Here is a group of users that's similar to the first one, but they do quite a bit more reading during the day. And here is a group of users who read very late at night. So they start reading after midnight, and they kind of read, into the early mornings. So what is this good for? It's very interesting, but what can we do with it? So here is a campaign that we did last week. We sent the first one of these kinds of emails, which is basically telling you a little bit about your reading habits and giving you a little bit of comparison to your cohort. So we can tell you things like how much hours you've read and the pages you've turned and the books you've finished. And we can also show you the average for people in your cohort and tell you something a little about yourself. So some people like it, some people don't. We're looking also at of how people are responding to this kind of information. Some people say that, I'm reading not as a sport. I just want to read for my enjoyment. I don't care about this statistics. And some people say, oh, this is really interesting. I had no idea I read, these hours of the day. That was my rate. That these are the number of books I finished. I also want to know more about what books I'm currently reading and so on. So it's interesting to see the replies we get from people about this type of campaign. And we're using all of this reading data and all of these cohorts that we're finding. So that was sort of a very quick run through some of the fun stuff we do at the big data team at Kobo. Before I wrap this up, I want to tell you a little bit more about deep learning. So deep learning is kind of a concept that's taking the machine learning world by a storm for the past 2 years or so. It ramped up over the past 5 or 6 years. So what is deep learning at a nutshell? So there's this idea of artificial neural networks. So we look at the brain. The brain is made up of neurons. They are connected, and the neuron gets input from other neurons, and then if there is enough input, it will fire its own output. And this is how all the computation is done. But it doesn't mean that we actually understand how, other than this mathematical formula, we don't really understand much more than that, or we're trying to investigate it. This is what neuroscience is about. So people have made these simplistic models with computers that represent the brain, and they call them artificial neural networks, and they've been doing it for at least 40 years. The problem is, if you think about it, it's something that's supposed to take an input, for example, a sensory input, some image, and provide an output, which is understanding who that person is, for example. And if you write it down in mathematical term, it's basically a very nonlinear function that has a lot of inputs, so a lot of numbers that are put in, but a lot of parameters, a lot of variables. And the problem is setting these variables to the right value. If I can get the variables to be, if I can set my parameters right, then I can predict accurately outputs for particular problems. The problem then is finding good settings for the parameters. And in technical terms, this is an optimization problem, and it's a hard optimization problem because it's a nonlinear function, because it's hard to figure out how to find good settings for thousands or millions of parameters. And so people have been struggling with this problem over the years because all artificial neural networks have a lot of parameters that need to be tuned. And deep learning is basically a strategy for doing that it finally seems to be working well. Now, how did we finally stumble upon this strategy? It relies heavily on being able to use a lot of computing power. It relies heavily in being able to use GPUs and to do a lot of massively parallel computation. Even then, it takes a lot of time to train a neural network, an artificial neural network. Sometimes it takes over a month just to run data through the system to tune these parameters. But we've basically come to the point where we have the right amount of computational power, as well as a way to do the optimization that seems to be working. And it does work amazingly well, and that made it something that's no longer just in the academic world. So it used to be a very academic problem. Mostly people in academia will discuss it and try to improve it. But now everyone uses it. Google Brain, Facebook, Baidu, Microsoft, and so on. So it's taking, it's a very successful technique for a lot of these problems that I was talking about. And it was actually one of the people who have never stopped working on this problem for over 40 years is Jeff Hinton, who is a university professor here at the computer science department. And over the years, he's had many students and postdocs who have gone on to become leading members of the machine learning world and of deep learning in particular. And so this kind of brings me to one last thing I wanted to touch upon, which is, where is this taking us? So this is Jeff Hinton, Jeff Hinton was my supervisor's supervisor, so he's my academic grandfather, and also a member of my committee. And he used to make a lot of fun of people who would, go off to industry. But finally, Google got him. So now he works part-time for Google, working on Google Brain and doing some amazing things over there, and part-time here. And who knows who this guy is? Say it loud. Yeah, so this is Elon Musk. So he's kind of like a visionary. He's the guy behind Tesla. He's the guy behind SpaceX. So he wants to put men on Mars and have clean driving. And these guys are in complete disagreement about this artificial intelligence techniques and deep learning and where we're going with that. So I encourage you to read a bit about it and form your own opinion as to whether or not machines are going to take over the world. But it's becoming sort of a common topic of conversation now. And finally, I have a question for you that has nothing to do with machine learning. It has a little bit to do with the lunar eclipse we had a couple of days ago. And whoever gets this right will get a Kobo device. So does anyone know who this is? It's not me. Yes?
I don't know her name, but I know what she did.
OK, what did she do?
I think she was the only female software engineer on the first Apollo mission, besides software on the moon.
Yeah, so that's pretty close. So I'll give you, so this goes to you. So this is Margaret Hamilton. I always like to ask a little bit of question that has to do with software engineering history. So she was the lead Apollo flight software engineer. She helped with the Apollo 11 lunar landing, and she's also credited with coining the term software engineer. So come to me after the talk, and I'll give you your Kobo device. And that's pretty much it for me. If you have any additional questions, let me know. Thank you for listening. Have a nice day.